Okay. Yeah, so as you will see, many of the things I will say have been already said here, especially regarding modal products and twisted convolutions, but I think this is a good thing to see these concepts popping up again and again. The three sections of this talk, I have divided it into a description of the Doppler-Fedenhagen-Roberts model. Then I will say a few words about renormalization. And then I will show you some examples we have computed. So let me start by explaining what the motivation for this work was. The Doppler, this Dfr quantum space is quite interesting because it is a quantum space-time, a model, a kind of quantum Minkowski space-time, but it has this particular feature that it carries a representation of the full Poincaré group, which is something I think interesting, because in this way we can keep the particle interpretation a la Wigner, so it is more easy to try to think about building a quantum field theory on this space-time. But once you are able to set up, let's say, for a quantum field, a free quantum field over this space-time, then of course the question about interactions appear, and then somehow you will be forced to think about renormalization. Now, as we know, in renormalization theory, there is a very close connection between causality, locality, and renormalizability. No? So, for instance, I will review a few of these concepts now, but for instance, in the Epstein-Glasser approach to renormalization, we know that causality plays a very important role in producing terms for the scattering matrix which are finite. No? So one question that appears here is the following. In the Dfr model, which is Poincaré covariant, we have, when we build a quantum field there, we have two Hilbert spaces. One Hilbert space associated to the quantum spacetime, and another one that should be in principle associated to the quantum field. Now, if we want to make contact with the more standard quantum field theory, somehow we have to, I like to call it a tracing out the space-time degrees of freedom. And when we do that, or better said, there is no Poincaré invariant way of doing that. So when we trace out these degrees of freedom, we are confronted with a non-local field theory. So causality and locality are lost somehow, and then the question of how to set up a renormalization scheme appears. So this is something that I want to discuss. There are many different possibilities, and a feature of this model, quantum spacetime, is that many equivalent ways of formulating renormalization or for constructing interactions in the commutative case will turn out to be inequivalent when we go to the non-commutative case. So we have chosen the one, we have found the simplest one, just to be able to compute a few examples and get some intuition about what is going on. So, well, this has already been mentioned now about this principle of gravitational stability. The main idea is just if we want to have a very good resolution of space-time events, we will at some point affect the structure of space-time, so it will lose operational meaning, and this is the motivation behind the introduction of space-time uncertainty relations. No? And this is linked to the question about what will happen then to locality. So the original uncertainty relations of the Dfr model were written in this form. The derivation was based on a linear approximation of gravity, but there is a more recent one by Tomasini and Biaggiu, which takes this form and is more, it takes more, it has hypotheses which are stronger, and in fact, the first set of inequalities can be obtained from the second one. No? So the question in this paper from '99 of Dfr, Fedenhagen, and Roberts was, is it possible to have some set of operators leading to this type of uncertainty relations? Of course, they very much look like Heisenberg's uncertainty relations, so a good idea is to start trying to look for operators which are as similar as possible as the ones we have in quantum mechanics. No? So the idea is to have a set of 4 operators, Q0, Q1, Q2, and Q3. These operators should, so the most important condition is they should transform covariantly under Poincare transformations. No? Now, since we don't know anything at this point about this algebra, we just postulate some commutation relations. We introduce a constant here, which is supposed to be of the order of the Planck length. And then Q is here just defined as the commutator. No? So what is the simplest possibility? Well, the simplest possibility, of course, is taking Q to be a constant matrix. That would lead us to the usual Model case. But as we know, if the Q's are to transform covariantly, then Q should be a second order tensor. So it cannot be a constant. No? So we are led then to a second simplest possibility, which is considering the big Q's to be central. So this was the second condition imposed, that the capital Q's should commute with all other elements. And then, once we know that Q should behave as a rank 2 tensor, then we more or less, and also knowing that it is central, then we immediately get to these 2 possible Lorentz invariants. So a way of constructing a model is just by demanding these invariants to be constant. We'll explain that in a minute. But once we do that, then it is fairly simple to come to the conclusion that the set of spectral values of the capital Q's will have this form. So it is a disconnected, a connected sum, disjoint union of 2 manifolds, which are homogeneous spaces for SL2. So how does this come about? Let us think we have one of the, so since we have these operators Q, we can consider spectral resolution, no? And one of the possible values would be a matrix which is antisymmetric, so we model it like an electromagnetic field, but this is just a name. And then once we have one of these, we can Lorentz transform to another frame, and then we find that the set of all possible values is given by an orbit, no? So the Lorentz group acting on the set of these matrices, and this is how we get to this set of spectral values, which is a manifold. And it is interesting because the conditions of normalization, so here we have these 2 invariants, and so we impose these 2 conditions. The first invariant should be 0, and the second one should be up to a sign just equal to 1. And then this forces the values of E and M to be non-zero. No? Actually, their norms, Euclidean norms, they have to be greater or equal than 1. And with a little work, then you can see that each one of these components is topologically the tangent bundle of a sphere. No? So this sphere, you can imagine it as being composed by these 2 vectors E and M. So with the sum and the cross product, you construct a point in the sphere and then a point in the tangent space to the sphere. And this will play an important role in what I am going to explain now.
Why do you choose those conditions?
These coefficients?
For now, equation 13 and 14?
Yes, because they are, I mean, these are the 2, if Q were an electromagnetic field, then these were the 2 possible invariants. No? So the simplest possibility for constructing a model is just to say, okay, I want an algebra where these Qs are central, and furthermore, they are invariant. I mean, their corresponding invariants are fixed. No? So, of course, you could put here just one constant and here another one, but in the end, what you get is a difference, and the more symmetrical choice is this one. No? But it is, of course, something put by hand. No? It's just a way to have a possibility of building up a model.
Why is E dot m not 0?
Huh?
E dot m. If it is 0. Why is it not 0?
No, this is imposed. This is an imposition. You impose that.
But m is a tangent. E is point on the sphere, and m is tangent to the sphere.
Yes.
These two vectors are normal.
No, they are not normal. No, you have. I mean, this is just an antisymmetric matrix, and you pick any two E and M fulfilling these two conditions. The set of all those M's and E's fulfilling these conditions is topologically the tangent bundle of a sphere. No? But the point is that this will be, I will show it later, this will be the set of spectral values of the operators Q. No? And this is just to get a bit of intuition about the model, and now I will explain how to actually construct these operators. No?
What is D?
Huh?
D.
D is the set of diagonal matrices in SL2C. No? Okay, so having this intuition more or less, we now consider these commutation relations in their Weil form. This is just the same as the usual Weil relations, with the difference, which is important, that Q is now not a constant but a central element of the algebra, which is to be found still. Now, if we fix the usual symplectic structure, just like this, sigma 0, then we know that we can take just two oscillators and construct the usual canonical commutation relations. And the interesting thing is that out of these commutation relations, we will end up with a set of operators which transform according to the Poincaré group. No? How this is done? Well, we just take these two oscillators and consider operators x0 to x3 defined just in this way. So of course they fulfill these canonical commutation relations with sigma fixed. No? But as we want operators which transform according to the Lorentz group, we now define a new Hilbert space where these operators are going to be acting. The Hilbert space is the following. This calligraphic L denotes the Lorentz group. So we consider square integrable functions from the Lorentz group to the Hilbert space of the two oscillators. This is, of course, almost the same as considering the product of the Lorentz group with R2, the configuration space of the two oscillators, and with this measure, this is the Haar measure in the Lorentz group and the Lebesgue measure in R2. Now, a vector in this Hilbert space HQ, which is the Hilbert space of this quantum spacetime, is a map sending a Lorentz transformation to a vector in the Hilbert space of the oscillators. And the inner product is just given by this expression. Now, just because of the way we have defined the Hilbert space, we can define operators, Q, now, acting on psi in this way. No? Just we take the old X and then we use the point where we evaluate the state to transform the position operators, or space-time operators. And we also get a unitary transformation giving a representation of the Lorentz group. No? Now, if we take these two expressions together, then we realize that in this way we can have a covariant representation. No? So the Qs will transform according to the Lorentz group. If we add another copy of oscillators, then we can implement the full Poincaré group. No? So it's just doubling this Hilbert space, and I have not written it, but it can be done. So now,
Andrejz,
yeah.
In equation 26, what is psi lambda on the right hand side?
This?
Yes.
So
did you define it already?
Yes. So here I am defining this Hilbert space. So an element in this Hilbert space is a function taking values in the Lorentz group. I mean, a function going from the Lorentz group to the Hilbert space of the oscillators. So as an element of this Hilbert space, this is a map from L, the Lorentz group, to the Hilbert space of the oscillators. So when I evaluate it at the point lambda, I get not a number, but a vector in the Hilbert space of the oscillators.
So there is a psi corresponding to the unit element of the Lorentz group?
To the element you started with.
So
Yes.
So psi lambda should be some u of lambda.
So this is a vector.
Yeah,
This is a state in the Hilbert space of the oscillators.
But with the label lambda,
It's a point in the Lorentz group.
yeah.
Just think of the Lorentz group as a space,
Yeah.
no? The base.
So in particular, there is a psi at the unit element of the Lorentz group.
Yes. Yes, but that doesn't have a particular.
That's fine.
Okay.
But so
Is this an equivariant map?
So the important thing is exactly that you can also let the Lorentz group act on this Hilbert space, and then these operators Q's will transform covariantly. This is the important point, which is a bit of a surprise, no? That you can just out of two oscillators get a representation of the Lorentz group, and this is what makes this model special. No? So with considering a second set of oscillators, you can make the full Poincaré group act on this. Okay, I will go through this very fast because this has been repeated at least twice today, but I will try to make a point with this. So let me come back to quantum mechanics and consider the modal product. So we start with the canonical commutation relations. We have the Weil form of these canonical commutation relations, which is associated to the canonical symplectic structure. So we can more abstractly define Weil generators fulfilling the Weil algebra, as we saw in the previous talk. And we can also consider this symplectic form as given by an antisymmetric matrix, which in this case fulfills these properties. Now, I just wanted to repeat once again the relation between these commutation relations and the modal product, which is to say, if we take the Fourier transform of a function in L2 of R, here I will use these conventions for Fourier transforms and their inverses, then I think this, I don't know who had this idea originally, but Modal, Weil, Wigner, of quantizing functions just by replacing these plane waves by the corresponding Weil generators. No? So in this way, we can just make a replacement of these plane waves by the Weil generators.
Groenewald.
Groenewald, Modal,
I think he
all these
was the
people.
first
Yes.
person.
Yes. Okay. So you do that, and then actually what we see is that, well, we get an operator. We have been, it has also been said here that when we take the closure of the set of these operators, we will get the compact operators. But also important is that we can induce the modal product just by demanding this map to be a homomorphism. No? So we have this identity, and then we look up for the result, so the symbol corresponding to the right side, and then we find the modal product, which I have written in three familiar ways. No? Okay, so now in the Dfr model, what we do is almost the same, with the difference that in this term, what we have is actually an element of the algebra. A central element, but it is not a constant. No? So that will make a bit of a difference. So two situations where we see this will be important. So for instance, we could think of defining the most easy or naive way of trying to define a quantum field over this space-time is just by repeating the trick. So in the Modal case, we have plane waves, and we replace them by the Weil generators. If we take the Fourier decomposition of a field here, we have these plane waves, and then we want the Q's to be operators, so we replace these plane waves by the corresponding Weil generators. But then we see that these operators will be acting on the Hilbert space we have just defined, and the creation and annihilation operators should be acting on a Fock space. So more or less, it makes sense to consider this Hilbert space as a tensor product of this form. No? Now, let us think, for instance, about trying to define an interaction. So I should consider this element squared. And if I do that, then I am forced to consider the product of these Weil generators. But since Q is not a constant, I see that these elements do not close to an algebra. So I have to consider something bigger. No? And the same concept can be expressed by saying that if I try to quantize functions using the same trick, no? Taking the Fourier transform and replacing the Fourier components by the Fourier waves by operators, then if I want to have a product, this works nicely in the Moyal case, but here I have to do something else because I will have the capital Q's there, so I have to include them somehow. No? So this is the statement. Now, since the Q's have a spectrum that goes through all these sigma manifold, then we see that it makes sense to consider an algebra of functions. Let us think of functions, continuous functions vanishing at infinity, taking values on the set of spectral values, which is this manifold SL2 over D, and taking values on integrable functions. Now we can just consider this type of functions. Upon taking closures, one can show that this will be a space of continuous maps from sigma to the compact operators. No? But we still want this relation to hold. No? So now we somehow induce a star product. And as said before, this star product contains not only the small q's but also the capital Q's. No? So just let me try to be a bit more explicit. So I take a function of this type, but notice the difference now. No? So f is not just an integrable function. It is a function from sigma to L1. No? So that means it takes values. I can put it like this. I consider this Fourier transform with respect to the x variables, but sigma is an element of the manifold of spectral values. And then I can think of decomposing Q through the spectral resolution in this form. So these are the set of all the sigma matrices I was mentioning. If I do that, then I can define a representation of this function through the symbol, and then put here operators fulfilling the postulated canonical relations. And then what we find is a star product, which, as you see, is not just a function of x, but it is also a function of sigma, so it is a map. No? So we always have to keep this set of spectral values into account. Okay, now the same thing, so we can think about this either in terms of a product or in terms of a twisted convolution. No? So for instance, if we want to think about it as a product, then we can induce a twisted product just by demanding this condition, and this will define a symbol. In this case, for instance, I have written down explicitly what the twisted convolution is. It's almost the same, but here, notice that this symbol depends on sigma. No? So it is a map from sigma to L1. Okay, so I won't be boring you more with this. This is an example, just the product of two such functions. So the main point is the following. The algebra generated by these operators, I can consider it as an abstract algebra, or I can consider it through the explicit representation I mentioned, which is the standpoint I will take. In any case, elements of this algebra can be thought of as functions of the capital Q's and the small q's. The capital Q's belong to the commutant, and that's it. Now, we would like to have a notion of integration, so to have some idea of how to do calculus here. We want to define interactions, so we need derivatives, we need integrations. In the previous talk, it was mentioned that there is a canonical trace given there, which in this case would amount to this expression. No? So actually here, we replace the operator Q by X and integrate, or another way to put it is just we take the symbol of this one and evaluate its Fourier transform at 0. This will define a notion of integral over space-time. But if we want to consider, for instance, the Dyson series, then we, sorry, how much time do I have?
10 minutes.
10 minutes?
Oh, no, sure.
It's from 4 to 4:50 is talk, right?
40? Okay.
Yeah.
20 minutes.
20 minutes.
20
okay.
minutes.
Okay, it's fine. Now, so we would also like to have a notion of integration over space slices, no? Now, this is a point which, I mean, one could discuss about this, the physical meaning of these operations, because I am introducing here a time coordinate. No? So this is a definition of what the integral over space at a fixed time is. It is given by this expression. So we take an element in the algebra, replace Q operators by position vectors, and then integrate over space. This will give an element in the center of the algebra, because we still keep this Q dependence. So this is something that could be argued against, but never mind, I will just take this definition. Important is that we have these two definitions of space integral and space-time integral, and the two of them are compatible. So if I take the first one and then integrate over time, I will get the first one. And this is the expression that one uses to define Dyson series, for instance. Now, I won't write explicit expressions, which are known in the original papers, but let me just say the following. If we take symbols, I mean, these functions, which are defined in terms of Q, so this one of these f of Q is just, maybe I can come back, of this form. So we take an element of L1, take its Fourier transform, and replace these plane waves by these generators. Then we get elements which are in the algebra, but they are not the most general elements in the algebra. No? Because if I take a product of two of them, I will get elements from the center. But so if I take the product of n of these functions, then what I end up with is with an element of the same algebra with the twisted convolution. This twisted convolution can be re-expressed in terms of a kernel Cn, such that the product in the algebra is given by a space-time integral of the symbols times a given kernel with values in the center of the algebra. So if we want to make contact with the usual quantum field theory, then setting up an interaction here is okay, but we still need to evaluate in some state of the space-time to get only elements in the Fock space. Now, for the space part of the integral, we have this other kernel, which can be obtained from the Cn kernel by integrating over space. No? And it also fulfills this type of property, so we have these kernels. Details are not important here for the computations, but conceptually I think it's important to mention that these kernels, of course, are non-local, introduce a non-locality, and this non-locality will be mirrored in any quantum field theory we construct over this space. Okay, so this was a review of the basic Dfr model. So now let me come to a few remarks about renormalization. Especially, I am interested in the relation between UV divergences and causality. So, if we go to the just naive form of Dyson series in terms of time-ordered products, then we have the definition of time-ordered product. In quantum mechanics, it's more or less in order, okay, there's no problem. But in quantum field theory, we have distributions, and then we are faced, just because of the use of these step functions and the deltas coming from the commutation relations, that we are faced with the problem of multiplication of distributions. No? So I will go very quickly through this example. Just if we try to multiply a step function by a delta function, well, we know we cannot do that, but we can insist on defining a product in space by means of this formula. No? So this again, this twisted the convolution against the product. So hoping that the convolution of the Fourier transforms will give us the Fourier transform of the product. If we insist in doing that, then of course we get an integral with a logarithmic divergence. No? So most of these divergences can be traced back to these two examples of this kind. So there is this idea of introducing a switching function, no? So in the interaction, and then using a causality condition of this type. Here I am thinking about quantum mechanics, so G should be a function of time, and this means that the support of G1 lies to the past of the support of G2, and the causality condition tells us that in this case the scattering matrix should factor in this way. No? So this is at the core of the Epstein-Glasser approach and also of the approach by Bogolyubov. Now, the three principles that are the input of the Epstein-Glasser approach are covariance under the Poincaré group, causality, and unitarity. No? In particular, causality leads to an iterative solution of the problem in the following sense. Here, we just give up the time-ordered product of the interaction. We just postulate certain operators Tn, and then the causality condition written in this form perturbatively will lead us to this kind of expression, which allows us to get T2 out of T1 and then T3 out of T2 and T1 and so on. So there is an iterative solution, and this is at the core of the Epstein-Glasser approach. Here I had written an example, but I think time will not allow me to discuss it in detail, but in quantum mechanics we can just use this kind of condition to see, for instance, that the T2 operator is just given by the time-ordered product of the T1 operators. No? But doing this in a proper way in quantum field theory requires to talk about splitting of distributions, extensions of distributions, everything. So the main point is the following. Since all of this relies so heavily on causality, what will happen when we go to a theory where we will lose this causality, no? Or these properties? So this was our original motivation. So trying to set up an approach like Epstein-Glasser for us was just out of the question. So then we thought maybe with Bphc, which is a formulation in momentum space, then, well, it has a solution through Zimmermann's forest formula, which is more direct, and then we thought of using that in this case. Now, this called our attention because there was a couple of works by people like Volgen and Schweda, I think, from 2013, where they explored Moyal models, no? So Euclidean field theories with the Moyal product, and they were trying to use this Taylor subtraction from the Bphc method, but then because of the UV-IR mixing, they were forced to change the subtraction prescription. No? So that means that just applying blindly the forest formula will not always work. No? Now, in the case of the interactions we considered, which is just considering a quantum field in the way I mentioned and taking the product using the rules of this algebra, and then averaging over the center of the algebra, well, in this way, the single terms that you get from the naive Dyson series are finite because of the constant we introduced, the lambda. Being finite, we can then be sure that if we apply the Taylor subtraction, the result is also finite, and then we can have control over the large scale limit and recover the usual quantum field theory. So here just a few words about the relation between dimensional regularization and Bphc. So let us think, for instance, in the usual case of a one loop contribution to the 4-point function of phi 4. So the interval you get has two inner lines, no? But with dimensional regularization we get such an expression. And this is just the same as what we get from the Bphc method using the Taylor subtraction. So this operator denotes a Taylor subtraction of order 0 with respect to the external momentum, which is P. Recall that the order of the Taylor subtraction is given by the superficial degree of divergence of the diagrams. So if we do the computations, then we end up with a formula which is almost the same as this. The only difference is that here, this is the parameter we introduce in dimensional regularization, whereas here, m is the mass of the field. No? But of course, we are given a freedom in the result by a polynomial of order the degree of divergence, because we are actually working with a momentum version of extensions of distributions. So we have this freedom, and we can use it to replace this m by the parameter mu, and then the two results coincide. Now, a more interesting example is a diagram with subdiagrams. No? So this is another example, a two-loop contribution. In this case, we can consider these different subdiagrams. Here we have 1, 2, 3 subdiagrams, which form the forest according to Zimmermann's formula. Then we can apply this Bogoliubov-R operation and get an integrand, which is just Taylor subtraction to order 0.
Maybe I misunderstood you.
Sorry?
Maybe I am not reading your diagram correctly, but this looks like a diagram from a quintic theory.
Sorry, yes, it should have been 5-4. I mean, I took the wrong diagram. Yes, it should be 2-point function.
5 vertex.
Yes, this is wrong.
Is it the correct
Okay.
set of the propagator?
Yes, I wanted only one. I only wanted to have. Never mind. Yes. Yes.
Only one external leg
Yes,
on
yes,
each side.
yes. But yes,
Okay, fine.
for the internal legs, it won't make a difference. Okay, but the internal diagrams, they have a degree of divergence 0, so we have one Taylor subtraction for each such subdiagram with these substitution rules, and then for the overall diagram, which is of order 2, we have this subtraction. So we compute it, and then we cannot again obtain a result which I have taken here to be looking as much as possible to the one in dimensional regularization. So we do this because now we want to do the same with a quantum field over the Dfr model, and our idea is that this has been argued before, of course, is that if this is to make sense in the large scale limit, so naively, if we take lambda p going to 0, we should recover the usual quantum field theory. No? So even if the Feynman diagrams we get with this model are finite, we should consider a finite renormalization in such a way that when taking the limit we get the known result. So this is a kind of benchmark for the computation. So now we come to the Dfr model. So as said before, we set up a quantum field in this way, and now we will have to evaluate. So we define interactions just by using the product in the algebra, but then we have to take make a choice of a state. These states will be states of optimal localization, as they are called, which are nothing more than coherent states of the corresponding oscillator. So they will allow us to localize as much as possible the space-time coordinates. We cannot do better than localizing them around the sphere. No? We had this set of spectral values, which was a tangent bundle of a sphere. They can be localized on a sphere, so we keep rotational invariance, but we lose Lorentz invariance. No? So this is how Lorentz invariance is lost when evaluating these average values. So the whole thing can be done. So a few comments. No? This breakdown of Poincare covariance or causality, locality, is a common feature of most models on non-commutative spacetimes, as we all know. Now our motivation, now given the strong implications of covariance and causality for perturbative renormalization, one is led to question whether the direct application of the forest formula is justified from a physical point of view. We are not attacking this question, we are just blindly trying to push a calculation to the end and see what can we learn about it. And as said before, there is this series of 2 works by Blaschke and company from 2013, where they show how applying the forest formula directly to the Moyal case leads to problems due to the ultraviolet infrared mixing. Now, in our case, as the diagrams are finite to start with, we won't have that problem, and then we are able to control the limit of large scale. So here I have an example of a second-order 2-point function in phi3 defined in the way I just mentioned. I stands for the integrand, so this is the integrand corresponding to that diagram as a function of momentum, of internal momentum. As you see, in the commutative case, the integrand will give a logarithmic divergence, which is given by the slow fall of this tail. The corresponding Taylor subtracted integrand is given by the orange line. Now I will consider the same situation, but in the case of the quantum field, of a quantum field over the Dfr model, and then we see that I have done this just to exaggerate. If I put lambda p at the scale of the mass of the field, then I can see clearly how, even if I don't consider any Taylor subtraction, the integrand falls very rapidly to 0. It will give a convergent integrand. No? So, but still I can consider a Taylor subtraction, and I will get this expression, and then I can think of studying what happens when I take lambda p to 0. I will recover the same result, so the orange line. Now, of course, lambda p mathematically is just a parameter here, but it has a physical meaning, so it should be of the order of the Planck scale. So we have computed so you compute the integral, so I gamma is the integrand and j is the integral. So if you compute the integral and fix lambda p to the Planck scale, then you get a finite result. Never mind how much is it, but it is finite. Now, if we let this lambda run more and more to 0, eventually this integral will diverge. No? And so this plot is showing this. In contrast, if we consider this finite Taylor subtraction, and then repeat again, letting this parameter run to the left, then we see that, well, it will, so this is log of lambda p, so this scale is more or less QCD scale, which is an exaggeration, but it's just in order to be able to picture it. But what we see is that, of course, the result we get cannot be distinguished from the result in the commutative case. It converges very rapidly to the commutative case. But, well, this is just to check that the way we have done it is compatible with the large scale limit. And the same can be done with the sunrise diagram, which is a second order 2-point function. I guess that was the one I wanted to put in the other slide. So here the complication is the following. As I showed, with forests, with the Bphc method, we have the forest formula. We have 3 subdiagrams with 0 degree of divergence, and 1 overall diagram with second order of divergence. In this case, well, there is a result by Zimmerman that tells us that actually the inner loops don't have to be considered, so there is a way of showing that, so that actually only the Taylor operator to second order has to be considered. This is a simplification, but if we go to the non-local theory, so this model we have been considering, then when you consider contractions and normal order and everything, then we just don't have the same symmetries that we had before, because we are averaging over the spectral values of the Qs, and then the amount of terms that pop up here run out of control. So this is something we wanted to just to explore, and of course this cannot be done analytically, not at least we were not able, so we had to do it numerically, and the amount of diagrams that appear, or the amount of terms corresponding to this diagram, is huge. So it is quite a work, but again, you can just compute them and check what happens in the large scale limit, and then we checked what happened with different values of the mass of the field. Of course, this is just a diagram that could be part of a bigger diagram, so the external momentum was set to a value which was convenient for the numerical computations, but one could explore more possibilities. So just to finish with a few remarks, the quantum spacetime of Doppler, Hagen, and Roberts is a well-defined, conceptually appealing model, which is fully Poincare covariant. Upon application of localization states, which I like to call partial trace over the space-time degrees of freedom, we obtain a non-local field theory model. Now, although the Feynman integrals for quantum fields on this space-time can be finite, the correct large-scale limit requires a finite renormalization. And then we have seen that Taylor subtraction following Bphc in the commutative case can be applied to this space-time. So in this talk, I have showed you some numerical computations we have done with this. Of course, one could argue that for particle physics, this is not very meaningful, but it is a matter of principle just to learn how to do quantum field theory on these models, and in this sense, I think this is an interesting exercise. Moreover, now we see more clearly that the actually interesting applications of this model could be in cosmological applications. So this is another reason to consider this kind of model. And now I am just guessing, but I just want to say a more rigorous approach to renormalization in the same Dfr model will be in the next talk by Gerardo Morcella. So, okay, that was everything. Thank you very much.